So chapter 12 is about liquid solids and intermolecular forces. And I like this quote from Roald Hoffman. It's a wild dance floor there at the molecular level, which is a good description of what individual molecules are doing, even say in a drop of water. There's a lot of activity going on there. We'll start out by watching a video. This is a video made on the space station. I believe this is a Canadian astronaut, and it's pretty interesting.
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung-out cloth? So, and had to use equipment that was here on board the space station. We might have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's packed it. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck and you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Merit and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I fill the water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth. Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet. It's becoming a tube of water. The water's all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is, the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jell-O on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
So that was an experiment, I believe, suggested by some probably like middle school students, or possibly high school students. But that's not how water behaves in gravity, is it? When you wring out a washcloth down here on Earth, what happens? The water falls to the ground, right? Or all over you. There, where there's no gravity to pull the water down, it just slides along his hands. You know, it's being forced out of the washcloth because he's squeezing it, but it's not going to leave his hands. It's just going to travel along and just keep moving until it, stops being pushed around. This picture here is that same guy, actually, and there's a water droplet Actually, it's a lot more than a droplet. That's a big bunch of water. And in the absence of gravity, the water will cluster together and it'll form a perfect sphere. You poke it and deform it, but eventually it'll reestablish its spherical form. So this behavior is caused by intermolecular forces, which are very important in the properties of matter. Here, the beginning of this word inter means between. So this is between molecule forces. And these are the forces of attraction that exist between all molecules and atoms. They are significant, though, only at very short distances. They are responsible for the very existence of liquids and solids. Without intermolecular forces, there would be no solids. There would be no liquids. Everything would be a gas. And they are also essential for physiological processes like enzyme-substrate interactions and replication of your DNA. All sorts of very important physiological processes depend on intermolecular forces. So the state of a sample of matter, whether it's a liquid, solid, or a gas, at a particular temperature depends on the relative strength of its intermolecular forces relative to the amount of thermal energy. And we're going to have some review of the three states of matter here. Here we have illustrations. Well, actually, let me just stop there because I should start a new video.